This is third and last module of chapter 9. In this module, we shall consider another important PD known as elliptic partial differential equation. The most common elliptic partial differential equations are Laplace equation and Poisson equation. These two equations are almost same. When the right hand side of Poisson equation is 0, then the equation is converted to Laplace equation. In this module, we shall describe the explicit method to solve Laplace equation as well as Poisson equation. We have mentioned that the most simple elliptic partial differential equations are Laplace and Poisson equations. The Laplace equation is nabla n u equal to 0 and Poisson equation is nabla n u equal to gr, where r is a vector containing the different space variables. Now let us consider two-dimensional Laplace equation, that means del 2 u del x2 plus del 2 u del y2 equal to 0 within the region R and u equal to f of xy on the boundary C. In this problem, both the variables are space variables, x and y are the space variables. Now we approximate the Laplace equation by the central difference approximation. So using the central difference approximation, the Laplace equation in two dimension becomes as in equation 2. Now we assume that the length of the subintervals along x and y directions are equal, that is h equal to k. So using this assumption, the equation 2 reduces to the following form. So note that this is a very simple equation, explicit equation, and from this equation we can find the value of uij if the values of u at the mesh point I plus 1 comma j, I minus 1 comma j, I comma j plus 1 and I comma j minus 1 are available. From this expression, it is seen that the values of uij is nothing but the average of the values of u at the mesh point, north point I comma j plus 1, east point I plus 1 comma j, south point I comma j minus 1 and west point I minus 1 comma j. The direction represents to the unknown mesh point I comma j. The known and unknown mesh points are shown in the following figure. The known points are denoted by field circle and unknown points or unknown meshes are mentioned by the ordinary circle. This formula is known as standard 5-point formula. Note that the four values in four direction are known, then we can calculate the medial value, that means the value of u at the point ij. So this diagram represents the mesh points, known and unknown meshes, in standard 5-point formula. It can be proved that the Laplace equation remains invariant under the coordinate axis or rotated at an angle 45 degree. So using this rotation, the above equation, that means the previous equation, is converted to the following equation as in equation 4. So this is another formula to calculate the value of uij, but in this formula we have to know the values of u I minus 1, j minus 1, u I plus 1 comma j minus 1, u I plus 1 comma j plus 1 and u I minus 1 comma j plus 1. If these four values are known, then we can calculate the value of uij as in previous formula, but this formula is known as diagonal 5 formula because these values, that means the known meshes are at the corner points of the square region. The known and unknown meshes for this formula are shown in the following figure. Note that the four corner values are available. If the four corner values are available, then we can calculate the value of u at the mesh point ij. Since the diagonal values are required to calculate the value at the middle point, so for this reason this method is known as diagonal 5-point formula. Now we consider Poisson equation. When the right hand side of the Laplace equation is non-zero, then the equation is known as Poisson equation. The two-dimensional Poisson equation is in the following form. del 2 u del x2 plus del 2 u del y2 equal to g of xy, where gxy is a given function of x and y. Obviously, the boundary conditions are given along the boundary C, where C is the boundary of the region R. Within the region, the differential equation is valid. Here we also assume that the mesh points in both x and y directions are uniform, that means h and k are equal. So, using this assumption and by central difference approximation, the equation 5 reduces to the following form. That means uij equal to 1 by 4 into ui minus 1 comma j plus ui plus 1 comma j plus ui comma j minus 1 plus ui comma j plus 1 minus h square into g I comma j, where g I comma j equal to g of xi comma yj. If g is a 0, then the formula 6 is nothing but the iteration scheme for the Laplace equation. Let u equal to 0 along the boundary C, then u 0 comma j equal to 0, u 4 comma j equal to 0 for all j equal to 0, 1, 2, 3, 4. We have divided the x and y direction into 4 equal sub intervals, and similarly u I comma 0 equal to 0, u I comma 4 equal to 0 for I equal to 0, 1, 2, 3, 4. So, using these boundary conditions, the known and unknown meshes for elliptic equation is shown in this diagram. Note that the lower boundary condition, upper boundary condition, left boundary condition and right boundary conditions are given. So, depending on this value, we can determine the values of the interior meshes, that means the value of u in the interior meshes. So, if we apply the 5 points diagonal formulas, that means by using the diagonal values, we can find the value of u situated at 2, 2 position, and using the value of u22 and other diagonal values, we can find the value of u33 and u11 and so on. So, using the 5-point diagonal 5 points formula or using the standard 5-point formula, we can find the values of u of the interior mesh points. Now, for a particular case, that means when I and j are taken as 1, 2, 3, then equation 6 becomes a system of 9 equations containing 9 unknowns. So, this is the particular case for the Poisson equations or Poisson approximation. Note that the coefficient matrix is constant. All the values are constant, 4, minus 1 are the values of the coefficient matrix, and this matrix contains a lot of zeros, and there are 9 unknowns u11, u12 up to u33, and right hand side depends on the value of g. So, solving this equation, we can find the values of u11, u12 to u33. This indicates that the equation 6 is a system of n equations, where n represents the number of sub-interval along x and y directions. Note that the coefficient matrix is symmetric, it is positive definite and sparse. A matrix is called sparse matrix if more than 70% elements are 0. Since the coefficient matrix is sparse, so it is suggested to use iterative method rather than the direct method to solve the above system of equations. Many iterative methods are available in literature to solve this type of equations. The commonly used iterative methods are Jacobi's method, Gauss-Seidel method, successive over relaxation method, alternate direction implicit method, etc. The first 3 methods are discussed in chapter 5. Now, we consider iterative method due to Jacobi's. The standard 5-point finite difference formula for the Poisson equation 5 is given by equation 8, that means uij equal to this expression. Let uij are with the rth iterated value of uij, where r equal to 1, 2, 3 and so on, then the Jacobi's iteration scheme to solve the system of equation 8 for the interior meshes is given by equation 9. Note that the values of r on the right hand side are taken as the rth iterated value. That means to calculate the r plus 1 iterated value of uij, we use the values of u available in the rth iteration. Now we consider Gauss-Seidel iteration method. In this method, the iteration scheme is given by equation 10. Note that the two values in the right hand side, two values of u in the right hand side are the values of the previous iteration, that means the rth iteration, and the other two values of u are the current iterated values, that means the iteration values at iteration r plus 1. So this is the modified form of the Jacobi's method, and this form is called Gauss-Seidel iteration scheme. It is observed that the rate of convergence of this method is twice as fast as the Jacobi's method. That means Gauss-Seidel methods give more faster convergence scheme than Jacobi's scheme. Now we consider another iterative method called the Successive over relaxation method or SOR method to accelerate the iteration scheme by introducing a scalar factor known as relaxation factor. This acceleration is made by making correction on the expression uij at r plus 1 iteration minus uij at r iteration. That means correction is made on the difference between uij at the r plus 1 iteration and rth iteration. Suppose uij at r plus 1 bar represents the value obtained from any iteration method, it may be Jacobi's method or Gauss-Seidel method. Then the updated value of uij at the rth iteration is given by the following formula. This is very interesting formula. uij at the r plus 1 iteration is equal to w into uij at r plus 1 iteration bar, this is the corrected value, plus 1 minus w into uij r. The second part is the new addition in successive over relaxation method, where w is called the relaxation factor. Now if w is strictly greater than 1, then the method is called over relaxation method. If w is exactly equal to 1, then the method is called Gauss-Seidel iteration method, and if w is less than 1, then the method is called under relaxation method. Now we discuss about the Jacobi's over relaxation method. For Poisson equation, the Jacobi's over relaxation scheme is uij at r plus 1 iteration equal to 1 by w into the terms appears in the Jacobi's method plus 1 minus w into uij r. So equation 12 is nothing but the Jacobi's over relaxation scheme. In this method, the first term is multiplied by w and the second term is the new addition to the Jacobi's method. The Gauss-Seidel over relaxation scheme is defined below. In this case, the first term is multiplied by w and the second term is the addition into the Gauss-Seidel iteration scheme. So this formula is also occurs as in case of Jacobi's over relaxation method. The rate of convergence of the above schema depends on the value of w and its value lies between 1 and 2. So generally we select the value of w is more than 1 but less than 2. So using the values of w, we can accelerate the rate of convergence of equation 12 or equation 13. But the choice of suitable w is a very difficult task. That means for different values of w, we get the different number of iterations to get the optimal solution. Two explicit methods called standard 5-point formula and diagonal 5-point formulas are described to solve Poisson equation as well as Laplace equation. And we have seen that this method obtain rough answer for Laplace and Poisson equation, but these rough values can be updated or modified by using iteration methods. So, we have described Jacobi's method, Gauss-Seidel methods and successive over relaxation method to modify the approximate value, and the over relaxation method is used to accelerate the rate of convergence by choosing the appropriate value of the relaxation factor W. Now, we consider Laplace equation, and this equation is to be solved by 5-point formula, and the result obtained by 5-point formulas are updated by Jacobi's method, Gauss-Seidel method and Gauss-Seidel successive over relaxation method. Obviously the Laplace equation in 2 dimension is del 2u del x2 plus del 2u del y2 equal to 0, and we have assumed that the region is bounded by 0, 1 along the x direction and also bounded by 0 and 1 along the y direction. The problem is to be solved by Jacobi's method, Gauss-Seidel method and Gauss-Seidel successive over relaxation method. In this case, the boundary values are taken as 0, 0, 0, 0, 0, 0 along the lower line, left vertical line, right vertical line, but in the top horizontal line the values are taken as 12.4 and 12.4. Note that in this method the diagonal values are not required if we use the standard 5-point formula. So, the boundary values are mentioned in the given grids or mesh points. First, we solve this equation by Jacobi's method. In this case, we assume that the initial values of u be zeros, all the initial values are taken as 0, but these initial values can also be determined by standard 5-point formula or diagonal 5-point formula. In this case, we also assume that h equal to k equal to 1/3. The Jacobi's iteration scheme is given by these 4 equations for the values of u11, u21, u12 and u22. Note that after substitution of the boundary values 0, 0 or 12.4 and 12.4, we simplified the 4 equations mentioned in the right side of the 4 equations. The first iterated values are u11 0, u21 equal to 0, u13 equal to 3.1 and u22 equal to 3.1. Now, all other iterated values are given in the following table. The first row, that means when r equal to 0, the initial values are taken as 0, 0, 0, 0. The first iterated values are 0, 0, 3.1 and 3.1, that one mentioned in first slide, and successive iteration are mentioned according to the formula of Jacobi's iteration scheme. After 16th iteration, we obtain the convergent solution for u11, u21, u12 and u22. Therefore, the value of u11 equal to 1.5500, u21 equal to 1.5500, u12 equal to 4.6500 and u22 equal to 4.6500, correct up to 4 decimal places. So, these are the values of u's, 4 u's obtained by Jacobi's iteration method. Now, we consider Gauss-Seidel's method. In this case also the initial values of the u21, u12, u22 and u11 are taken as 0, and also in this case h equal to k equal to 1/3. The Gauss-Seidel's iteration scheme is given by these 4 equations u11, u21, u12 and u22. When r equal to 0, we obtain the first approximate value of the variables u11 and so on, and the value of u11 is 0, u21 equal to 0, u12 equal to 3.1, same as the Jacobi's method, but the value of u22 is equal to 3.875. In Jacobi's method, we get the value of u22 equal to 3.1, but in this case the value is changed because the formula is changed for u22. That is why the value is also changed in this case. These are the first iterated values obtained by Gauss-Seidel's method. The successive iterations are shown in the following table. First row represents the initial value, second row represents the first iterated value, and after 11th iteration we get the convergent solution for the given equation. In Jacobi's method we obtain the optimal solution or the solution correct up to 5 decimal places after 16 iteration, but in Jacobi's method, Gauss-Seidel method, we obtain the same solution after 11th iteration. In this case also the value of U11 equal to 155,000, U21 equal to 1.55,000, U12 equal to 4.65,000, and U22 equal to 4.65,000. So these are the values correct up to 5 decimal places. Now we consider Gauss-Seidel successive over relaxation method. In this case also the initial values are zeros, and the SOR scheme, that means successive over relaxation scheme for interior meshes, are given by this expression. For j equal to 1 and 2 and I equal to 1 and 2, the formulas are this one. These 4 formulas gives the values of U11, U21, U12 and U22. Now we consider the value of W, that means the value of the relaxation factor W equal to 1.1. Then the values of U's, that means the value of U11, value of U21, value of U12 and value of 22 are mentioned in the table. Note that these values, that means the values of U11, U21, U12 and U22 converge at the 7th iteration. And finally the solution is U11 equal to 1.55,000, U21 is also 1.55,000, U12 equal to 4.65,000 and U22 equal to 4.65,000, correct up to 5 decimal places. Note that for the relaxation factor W equal to 1.1, we get the optimal solution at 7 iteration. Gauss-Seidel method takes 11 iteration and Jacobi's method takes 16 iteration. But the choice of W for successive over relaxation method is a very difficult task, but the appropriate value of W gives the faster convergence iteration scheme. Now we consider another example. That one is Poisson equation. Now we consider Poisson equation del 2u del x2 plus del 2u del y2 equal to 5x square y. Here also the boundary conditions are same, that means x is bounded by 0, 1, y is also bounded by 0, 1 and the value of h is taken as 1 by 3. This is also the value of k, and the values of u on the boundary are everywhere 0, that means u equal to 0 on the each mesh point on the boundary. We have to solve this problem using Gauss-Seidel method as well as Gauss-Seidel's successive over relaxation method. In this case g of xy equal to 5 into x square y and h equal to k equal to 1/3, and the boundary conditions are zeros for all subscript of u. Now we consider the Gauss-Seidel iteration scheme. This is the Gauss-Seidel iteration scheme. The last term is added as minus h square g of ih comma jk, and for this function g of ih comma jk equal to 5 into h cube I square j, and which is equal to 5 by 27 into I square j, because h is equal to 1/3. Thus, the iteration scheme for U11, U21, U12 and U22 are given by these 4 equations. Now, we assume that the initial values of U21, U22 and U12 are 0, and all other calculations are shown in the following table. That means, this table gives the values of U11, U21, U12 and U22. After 7th iteration, we get the optimal solution. and the solution is U11 equal to minus 0.02314, correct up to 5 decimal places, U21 equal to minus 0.04115, U12 equal to minus 0.03086, and U22 equal to minus 0.05915. So after 7th iteration using Gauss-Seidel iteration scheme, we obtain the solution of the given Poisson equation, correct up to 5 decimal places. Now we consider successive over relaxation method. The iteration scheme of this method is given by this expression. In this method, the relaxation factor W is introduced, and in this method we assume that the boundary conditions are zeros, that means U21, U12 and U22 all are zeros, and the relaxation factor is chosen as W equal to 1.1. So using this relaxation factor, the iteration scheme gives the optimal solution after 6th iteration. That means we get the value of U11 is minus 0.0231615, U21 equal to minus 0.04115, U12 equal to minus 0.03086, and U22 equal to minus 0.05916. All these values are correct up to 5 decimal places. Note that the values obtained in Gauss-Seidel iteration methods and value obtained by successive iteration methods are same, exactly same, but the Gauss-Seidel iteration scheme takes 7 iteration, while the successive over relaxation scheme takes only 6 iteration. By appropriate choice of W, the iteration number of iteration may be less than the number of iteration required in this table or for the value of W equal to 1.1. So we can conclude that the successive over relaxation method gives faster convergent result than the other methods. In this chapter, finite difference method is used to solve partial differential equations. Particularly, we consider the second order partial differential equation, for example, parabolic partial differential equation, hyperbolic partial differential equation and elliptic partial differential equation. Only the finite difference method such as explicit finite difference method, implicit finite difference method are used to solve partial differential equations. But many efficient methods are also available in literature to solve partial differential equations. Among them, the finite surface method, finite volume method are widely used.